Very glad to be here, and thanks for coming. So today I'm going to talk about some work I've been doing at Berkeley over the past 1 year and a half I am very excited about. And it's mainly focused, what I'm going to present today, of using machine learning to design better systems. So we are all here because AI, ML has been hugely successful over the past decade. But if you look at the application where AI has been particularly successful, it's in these human tasks, right? There excels now at speech recognition, image recognition, language translation, and in many of these cases, or playing games, and many of these cases is doing better than humans. But one thing about the human task is that 100% accuracy is not expected, because humans are not 100% accurate. However, when we are starting to apply machine learning and AI to systems, things are a little bit different. If you think about program synthesis, packet classification, controlling a system, then in those cases, in many cases, people expect that the algorithm, the particular control, or the particular decision we are making to be correct and also explainable. Okay, if when a decision is made, you want to know why the decision has been made. And it's not only in systems, but in other kind of application, like for instance, in mortgage, if someone, if you apply for a mortgage and you are denied, you can ask why you're denied, and the bank who denied you has to explain you why, because he needs to make sure that you need to prove you that he didn't use some discriminatory features to deny you the mortgage. So this is very important. So this is what I'm going to talk about how to use machine learning to build these kind of solutions. And there are three approaches we looked at over the past, again, 1-2 years. And one is pretty clear. It's like one is what I call iterative refinement, and this is about using machine learning and AI for optimizing a particular system. And in this case, you are starting with a solution which is correct, which was generated by some classic algorithms, and then you are iteratively refining it. Like, for instance, compiler optimization, like I'm going to talk about, or query optimization. So with each transformation, then it's guaranteed to preserve the correctness of the solution. The second one, it's correct by construction. So there are cases in which you can guarantee that the solution you are going to build using AI is actually correct. And the last one, it's generate and verify. And basically, this uses machine learning to generate a bunch of solutions, but then you have the ability to verify whether the solutions are correct or not, at least to convince yourself about the correctness. So the first one category is mostly like I mentioned, it's about optimization. The second two are about synthesizing. And during this talk, I'm going to give a few examples for each of these approaches. So let me start with iterative refinement. And here I'm going to start with compiler optimization. The compiler optimization, as you know, it's a very old discipline. It's 40, 50 years ago. So people really try very hard to optimize our code. So it's a pretty high bar to improve on these compilers. And as you know, when you compile a program, you have typically you have a set of optimization phases you apply to the program and each phase it's implementing a particular form of a particular optimization. And there are many such phases. In LLVM, I believe today you have around 90. And there are two questions here, is that which passes you are going to apply to a given program, and in which order you are going to apply these phases. And there are a huge number of possibilities here, okay? And let me just give an example to illustrate why the order in which you apply the phases, the optimization phases, matter. So here it's a very simple example in which you normalize an input to a L2 norm, and one possible optimization here is what is called this loop invariant code motion. And this is clear is that if you have something inside the loop which is not, remains constant over the entire duration of each iteration, you can take that variable and pull it off. Right? So in this case, you see the L2 norm. It doesn't change in the loop, so you can actually pull it out of the loop. Right? And another typical optimization is inline. So when you are going to call a function, so in this case L2 norm, you are going to, there is certain overhead in calling that function, passing the arguments, getting the results, and so forth. So if you inline the function, so you execute the code, inline in the same place, you avoid this overhead of calling, of function calling returning parameters, right? And the overhead here, after you've done that, is O(n). N is a number of iterations. Okay, but now let's assume that we are going to apply these two optimization phases in reverse order. So first we are going to apply inline. If we apply inline, then we are going to take L2 norm and you are going to expand it. So instead of calling L2 norm, we are going to inline the code for L2 norm. And now, but now then, if we apply loop invariant code motion, this optimization is looking at this code and it's only seeing that sum. It doesn't change. The initialization of the sum doesn't change in the loop. So it's just going to take that sum and move it up, the assignment. Right? It's an optimization, but obviously it's not a great optimization. But because you applied first in line, then now you are stuck with a program which instead of being n, O of n, it's O of n squared, because now inside the loop, each loop, you are also going to have another loop to compute the L2 norm. Okay? Just a simple illustration why the order matters. So to solve this problem, we use RL, and here is the RL formulation. So first, it's what is a state. So for state, we use 50 static features, which is a number of instructions, a number of loops, and things like that. And then we also use a histogram, a path histogram. So basically, you have this certain number of passes. In this case, we have used up to 45 passes. And whenever we apply a pass, we increment the corresponding index in that histogram, right? I'll give you an example. Actions, obviously, it's optimizer pass, which pass you are going to pick next. And obviously, the reward is the running time, by how much you improve the running time, right? It's quite natural. So here is an example. So here it's the state. You have, say, we will only look at the number of loops and the number of instructions, 3 and 20 is the past state. And also is this a histogram down there. So you are looking at 3 phases here, this loop invariant code motion inline, and just going aggressively using registers for variables which are used often. Okay, mem to reg. Okay, so now you basically say you take an action. So say you decide to use first the loop invariant code motion. Now you see in the histogram, I have 1 now because I applied this optimization. Now I also have there 100 cycles. In this case, say the running time. So the running time decreased a little bit to 99 cycles. Then I pick again another one. It's mem to reg. So this is another optimization. So again, I modify the histogram, and now I go down to 66 cycles. And finally, I use also inline, and now I go down to 56 cycles. While here I am using an optimization pass only once, it's actually, this is not necessary. You can use an optimization pass multiple times. This allows you, the algorithm. And you go to 56 cycles, so this is reward is 44 cycles because initially it was 100 cycles. Okay, so that's what it is. So this is an example of iterative refining because it's, again, you are going to start with a program which hopefully was correctly generated by the compiler, and now you're applying optimization phases. And these optimization phases are guaranteed, or better, they should be guaranteed that they preserve the correctness of the program. Right? The only thing where they change is the running time. Okay? We used to evaluate CA-Stone benchmark. As a baseline, we use a variety. As I mentioned to you, this is a very old field, 40, 50 years, so people try everything under the sun. Open Tuner is a tool using multi-arm bandits, obviously genetic algorithms, random. And -03 is what you are using today in the compilers by default if you want an optimized program for speed. This is a default. As a policy, we use a pretty simple network, fully connected. And for algorithms, we are using a bunch of algorithms we tested with proximal policy optimization, A3C, evolution strategy, and so forth. Okay? We use, in all the experiments I'm going to show in this talk, we used the system we built at Berkeley, Ray, which is a distributed computing framework, which has Python bindings, also Java. And on top of it, we have a bunch of very scalable libraries, like reinforcement learning library, RLib, and hypermeter search. And just a few more words, it's quite popular today, this system. It's in terms of growth, adoption growth, it's up there with best distributed frameworks, open source distributed frameworks, and so you can give it a try if you have this kind of problems. And so what are the results? So here are the results for our benchmark. So here are two y-axes. Apologize for that. On the x-axis, obviously, you have different algorithms you are using. And on the y-axis to the left, you have the improvements over the baseline, which is -03, what the compilers use today. Positive bars obviously means improvements. Negative bars means you do worse. And on the right-hand side axis, y-axis, you have the samples, how many samples you use to train for a particular program. So obviously, the smaller numbers of samples, the better. The higher the bar, the better, right? And the summary here that we are basically match the state of the art in terms of the performance. This is Open Tuner, which was it's used multi-arm bandits, and but with fewer samplers. But what we do much significantly better than OpenTuner is generalization. We see multi-arm bandit, you really cannot generalize. But we can generalize, and here are some examples. So generalization results. And we just train on 100 randomly generated programs, and then we test on this CH-Stone. We evaluate on CH-Stone benchmark and another 12,000 randomly generated programs, and we do a single rollout for each program to evaluate. And when you do that, on average, you improve by 6%. And again, for the compiler people, even 2-3% is a big deal, right? So now, so far, I've shown you how you are going to figure, you are going to find a good way to select which optimization phases you are going to apply and how to order them. But each optimization phase, actually, is quite complex in itself. It has multiple parameters. So now I'm going to talk a little bit about how we are going to choose the parameters, the arguments of an optimization phase. Again, let's take a simple example. This is just doing an addition between two vectors. And each of these instructions in the loop is basically two loads, an addition, two loads, an add, and a store. And what you can do here, especially in this case, because there is no dependencies between different iterations, you can, of course, parallelize, so called vectorize. And you can also pipeline, the execution of different operations. And actually, when the compiler generates code, it also generates the parameters for these optimization passes. So in this particular case, I'm showing it's pragma, which provides a looked vectorization width, so how many are in parallel, how many iterations you execute in parallel for, and interleave count, it's about 2, how you interleave the instruction. Okay? This is what -03 doing. Now, the funny thing is that, obviously, if you do the brute force, and you can do brute force in this case, to try all the possible parameters, you are going to do better, and these are the parameters which are doing the best. The vectorization width is 8, and interleave factor count is 4. But the funniest thing is that if you are trying, at least for these simple examples, you try all the possible combination of all the arguments, then in 27 out of 35 possible combination, you actually do better than the default. The baseline there, it's the first bar. And again, you have 35 possible combination of these arguments, parameters. and 27 you do better. So it's again, this basically says that it's room for improvement. So for that, to choose these parameters, to select these parameters, we build this neurovectorizer. And here I'm also showing you the system. So basically, you have the program. Then you do loop detection, and you extract loops. And then you use code2vec to do some code embedding, so to represent the state of the environment to the agent. Right? On the agent, we are using, again, PPO, proximal policy optimization. And this PPO, the agent will pick these two factors, okay? The vectorization factor, interleave factor, okay? And typically for vectorization factor, interleave factor, you use a power of 2, right? 1 to 4 and so forth. So to reduce the number of choices. And then you apply that, you apply the optimization pass, you run it, and now you are going to get the reward. And again, in this case, the reward is the improvement, but it's a relative improvement to use here. Okay? So it's pretty simple. It's again, obviously, it's an iterative refinement. The pragma do not affect the code correctness, right? You just so now, how do you evaluate this? Actually, this was a big problem. And to evaluate, we generate a synthetic data set. And that's because there is no good data set. Of course, one possible thing you can do, you can take one of these existing benchmarks, like SPEC 2017, and then you are starting to change the parameters for the loops, and then run it and see how it performs, right? So you can definitely do that. The problem is take a lot of time, and there are not enough loops in these benchmarks. And also, it's hard to, in some cases, to isolate the speed up. So that's why we generate some synthetic data sets. And I'm going to say more about this. So this is an important aspect. So in this particular case, one question is about you can also use supervised learning, right? It's like you look at the state, you look at the number of loops, whatever, and you say these are the parameters. However, if you think about the supervised learning, you need the labels. So you need to run to get these labels. You need to run all this brute force almost to get get the labels, right? Because I know that for this program, if I run it, I get this 135 cycles. However, if you use RL, you don't need to know the absolute value. You don't need to know whether only this set parameter configuration performs better than the other parameter configuration. And this helps us to converge much faster. OK, so how is doing? This is some LLVM benchmarks. It's again, you see the differences are small here. And this is a bunch of other baselines. The summary here that we are going to do, we are doing is 97% out, it's only 3% lower than the brute force. And compared with the baseline, which again it's minus 0.3, we are doing 2.6 better. And here is the things I was talking about. This is the number of compilation or samples we need in order to get these good results. So this is a normalized average performance. Remember, it was 2.6 compared with the baseline. And this is we compared with the supervised algorithms. And as you can see, the supervised requires a lot of more samples because you need, again, to get these labels. So, for instance, to get to the same improvements, like for RL, you need 15 times more samples, 14 times more samples. Okay? So I have only another 10 minutes to go through the other two examples I have. And I presented some early version of this last year, so I'm going just to show you some of the new results. And the second example, the second approach was correct by construction, right? And here, actually, I really like this example. And this is packet classification, right? Packet classification is a fundamental building block you have in almost all today's routers, firewalls, and things like that, right? And you use this for providing better quality of service, intrusion detections, to send a packet to an intrusion detection box, to drop packets, and things like that. Okay? And the way it's implemented, you have a set of rules, and the set of rules obviously has a predicate, which is looking at the packet header, and the packet header consists of the source and destination IP addresses, source and destination port numbers, and the protocol type. And based on that, it decides it takes an action, drops the packet, treats the packet with a higher priority, and things like that. Right? Now, the problem is that you have a lot of rules in general, and these rules, they have to be executed at the line speed. You need to execute this, you need to do this classification in microseconds, right? So that's the big problem. Now, this problem is similar with this point location problem in a hypercube. So basically there I'm using only I'm giving only the destination and source IP addresses. And if you look at what a rule represents there, it's a rectangle, right? Because it's a range in the source address and the range in the destination address. And what a packet is represented, it's represented as a point, right? Because a particular source address, a particular destination address, right? And it turns out it's a very hard time-space trade-off here. If you have AND rules and you have D, where D is, let me just show you. D is the number of fields in the packet header, so D number of dimensions. If you want to get optimal running time, this is log n in the number, because it's classification tray, log n in the number of rules. Then the space complexity, it's exponential in the dimension. And if you want to get optimal time, which is O of n, then the running time is exponential in the number of dimension with respect to the log of the number of rules. So none of this is working. It's not good. So what do people do? It's obviously there is a hardware solution which uses ternary CAMs, associative memories, but these are very power hungry. They are expensive. So as a result, people developed for the last 2 years a bunch of heuristics to solve this problem and to compute this decision tree, basically, right? Right? It's basically you get a packet and you want to find the rules to apply to that packet. And here it's when we started this, again, the one solution, one natural solution, if you apply machine learning, is basically saying, well, I have a neural network. This is a classification problem, so I'm going to learn, to this classification, and then I'm going to apply to new packets. The problem with this one, it's exactly that, is that there are multiple problems with this one. One problem is that it's not 100% accurate, and here you have security applications, right? I'm looking at the packets, and I need to, for sure, these packets come from this address to send to the intrusion detection box. So you cannot do that. The other one, good luck of having a neural network and implementing in today's hardware, which is going to make the decision in a microsecond or something like that, right? So instead what we do, we use the neural networks to build a classification tree. Okay, so this is what we do. And this is a lot of advantages, because this classification tree, once I build it, I can feed it into the routers. Let me go a little bit quicker now. We use proximal policy optimization, and this is how you do the state. We start with one node. One node has all the rules, and then we start to revise the space. And this is equivalent to adding more nodes to this hierarchy, where each node now is responsible for fewer rules, right? And this is the actions about, again, how you decide to divide each of the nodes to have fewer rules per node. And the reward, we care about two things, the running time and the memory size, right? And it's a linear combination between the two. It is correct by construction because you are guaranteed that the decision tree is always correct. You start with a node which includes all the rules, then you divide the node, and then you divide the number of rules, and so forth. So what are the results? Well, is a classification time. When we do that, when we use these neurocuts, this is the name of the algorithms, it's 18% faster than the state of the art. It's, again, a good number in this field. But if you, again, you have two metrics here, the running time and the memory. If you just make a constraint and say, OK, look at all the algorithms which use this amount of memory, then we are 3x better. If you constrain on the running time, say use all these algorithms have this kind of running time, we are 3x better, at least 3x better in terms of memory. OK? So pretty good results. And again, this you can use today. Finally, generate and verify out of pandas. It's another project I'm quite excited, and we work for the past 2 years. And it's not easy. And the problem it tries to solve here is today you have an API explosion, right? It's like when you write your programs, you just call a bunch of APIs, right? Probably there are more API calls than new lines of code, right? Like for instance, the problem is that when you look at this API, it's a huge number of functions, right? And when you look at one functions, they are very complicated with many dependencies between parameters and so forth. So what do, right, when you want to use? You do two things, typically. One, if your friend knows this API, you ask a friend how I'm doing X or how I'm doing Y. Or you go to Stack Overflow, right? That's what you do, right? The Stack Overflow, you say, oh, this is this Panda, so I want to turn this kind of data frame in that data frame. How do I do it, right? And with this one, as you know, sometimes, inefficient solutions, and then you don't get the answer right away, and when you need it, right? So, right? So with AutoPandas, what we want is basically think about like automatic Stack Overflows, in which you are going to ask the questions about how to do something with a particular API, and you get the answer. You get a snippet of code to do that thing, hopefully very fast. That's a vision. We are not there, but that's a vision. Okay? So again, we are looking at Pandas, the most premier library for data scientists, 300 functions, more than 300 functions. And even if you look at the programs which consist of one function, one API call, there are 10 power 17 possible programs. Okay? So how do we do that? It's again, this is an example of generate and verify. So you can probably predict what the solution is. So typically, this thing is for these pandas, typically the way that people ask, they actually naturally give the input and the output, input-output example. I say, this is the input, I want to turn this into this output. This is what I want the result to look like. Okay? So this is an example. And so therefore, AutoPandas is going to start generating small pandas programs, and then feed the input to that program, and look at the output and check whether the output is the output which was desired by the user, right? If it matches, this is one possible answer. If not, you go and search and search and search until you get something which takes the input and computes the desired output. Okay? So how do we do it? For encoding, we use graph-based encoding. So you see a set of, if you look at this input and output, you see a set of cells. So the cells which have some relation between them, that relation is represented by arrows in that graph. So for instance, in that graph, you see on the left-hand side, you have the yellow nodes. This is represented to the input, then the gray nodes, which are represented to the output. We have, I think, the orange edges represent the adjacency between the nodes. And for instance, you have weight in that particular cell in the input, and the weight in the particular cell of the output. You draw one of these blue edges. So that's encoding. And then, of course, we have a graph encoding. We use graph neural networks to come up with the program. But it's still a huge search space. So the trick we do here, and I think this is something you can do in many applications, it's you basically, you use domain expertise to reduce the search space. Right? So basically, there are, in many cases, like for instance, in one particular example, it's a drop. It's a drop function, for instance, in pandas. And the first argument of the drop, it tells you whether you drop a column or a row. right? So you can encode their constraints in what we call the generators for that particular API and reduce the search space, right? If it's 0, you know that it's a column. If it's 1, you know it's a row. Otherwise, you need to try all the possible combinations. So I'm not going to go into details, but you know, we write the generators, and then for each of the where we need to choose, we have the select functions, and the select function is is backed by a neural network. Right? So for one function now, we reduce the search space from 10 power 70 to 10 power 5. So it's much better now. And this is, again, generate and verify. You repeatedly generate solutions and verify the solution until we get a correct solution. Of course, here I'm cheating a little bit because I'm giving you as a program, I cannot prove the correctness. I can only say that for this input you can create the output, but I don't know whether it's exactly what you wanted. But the point here is that if you see a small program, in this case a few function calls, a few API calls, you can probably convince yourself that this is what I wanted. Right? It's much easier when you see the solution to convince yourself that it's a good solution than if you don't know the solution. So we really, you know, it's like this is, and this is, I'll be done very shortly. So we look, getting data to test for testing evaluation is very hard, right? There is no such data set. So we just grabbed the Stack Overflow and collected these 26 real-world Stack Overflow benchmarks. This is the tables with the results. You don't need to read all the numbers. I'm going to show you what are the most important ones. The bottom line, we could solve 65% of these benchmarks. It's, again, still a lot of things to do, but we're making progress. We also can find programs containing 3 function sequences. So programs calling 3, you know, is a snippet. The solution has 3 API calls. And why is this important, these 3? Because 90% of accepted answers in Stack Overflow contains up to 3 functions, right? So you have a big coverage. Because if the API is very powerful, the beauty of it, you don't need a lot of API calls, right? And most solutions are found in the top 2 function sequences we explored. So in all cases but 1. Okay? So again, in summary, I think that you know, when we are talking about machine learning and deep learning in particular, one of challenges we are always struggle with is about correctness, to prove the correctness and to understand or to explain what the program is doing. And you see a lot of work on that. So in this talk, I'm just proposing this kind of different approach to achieve these goals about correctness and explainability. So instead of using machine learning end-to-end, we use it to generate classic solutions, right? Whether it's a data structures, whether there are, you know, it's a program or a set of rules. And because with these artifacts, with classic artifacts, you can much easier to prove the correctness. In some cases, we can automatically prove it. And obviously, a set of rules or a program is far more explainable than a neural network. Thank you. And the last one, I just want to announce we have this Ray Summit. So hopefully, you know, coronavirus will subside by then. And, you know, we will wait for you there. Thank you.
Thank you, Jan. I have one question, actually. So the programs that are synthesized, there was one step in there that said check input output. So this means that you have a list of examples for the programs running?
Yes.
And then if the program has some behavior where its behavior is erratic on the areas that your input-output checks haven't explored, then that's a whole other problem to be solved to double check that you're actually generating.
There are a few things, you know, like it's actually a good question. It's like, so one particular thing which is very interesting there is that you need to be very careful because you have input and output. You know, I can generate, in Pandas, I can generate any output by just putting by hand, right, to filling every cell in the output. So we have some rules there. So basically, for instance, we give you the result, the code which has the fewest parameters, the fewest constants.
I see.
That's one thing. The other big challenge, I think, maybe alluded to that, is very hard to come with the training data sets, because you can generate arbitrary programs, but many of them make no sense, right? So then you don't learn the right thing. That's another big challenge. Yeah, thanks.
All right, let's thank Jan one more time. He will be around if you have any other questions.